I need to. No, how do we go down? Ah. Oop.
Number one.
Oh, fuck. Nope. Oh, I get the okay, if this is where I am, and I want to be on the PC. There we go. Hi. I get here early, so I can do this when it's quiet.
Yeah.
Because like at work, I can't do anything with people staring at me.
So,
I-
yeah, I was tempted to see, I came here early too. I was tempted to see if I can get everything hooked to my laptop.
Oh,
Because
okay.
so I have it set up to play stuff off of YouTube, and I'm
Okay,
not sure it'll transfer over like
okay. All right.
other thing.
Make sure this is on, because the other night I didn't remember where the. Okay, good, that is on. Okay, yeah, because I see that you have a slide presentation in here.
Yeah.
Okay,
So I might try to fill the whole system.
all right, we'll let you, the Zoom is up and everything,
Right.
so. So we could probably get out of this file that's there and close that for a second. That's a bit of speakers away. Okay. Yep. They're both back. So this is a good thing.
Always test the mics before the thing starts.
Well, on Wednesday I was by myself doing all
Oh, really?
this in the evening, and then there was like almost 60 people here, and I couldn't get the mics on. But thank God Leo was here, and it was the power button, because I'm like,
Oh, yeah.
I can't figure out what the power button
Yeah,
is.
never trust the right.
Oh my God. All right, so you can figure it.
Yeah, I'll give it a shot.
So you do this, so you can.
I'm having a bad technology morning already,
Uh-oh.
but
Oh, no.
but hopefully I'm glad that this is here just in case, right? Like,
Well, that's okay, because the movie was up from Friday night, was still there, and I'm like, oh, I turned this movie off. Like, where is my ex? Where is my ex? I will say that the one thing that COVID did
Mhm.
made us better at
Oh
technology.
yeah, like Zoom used to be kind of like mysterious, and now everyone's like, oh, like
Well, and I would be on the phone, like when we went to work from home, it make sure was everything working, with the family working
Right.
from home, was everything else, and how to explain to somebody how to get out and do their documents.
there.
You got it?
Yeah, I was just looking for the Zoom link. It takes a second to find sometimes.
All right.
And I'm on.
Morning. So yeah, the Zoom, oh, look at that.
Is Ryan, have you seen Ryan?
Yep. Ryan is here.
Ryan is here?
Yes, Ryan is here.
That's good.
Do you need a little table?
Yeah, I need the little table. Good morning, Josh.
I can give you the. Why is it
Be here. Where is your?
Well, I can go tell you, you need a card table, right?
I'm sorry.
You need a card table? I can go tell you. It's got to be your.
He usually puts
Seems to be. I still co-host already. Now I should have. So let's see. So the meeting now is on. The sound seems to be on. And I'm not echoing. Am I? I'm not echoing.
Turn down, maybe the volume on.
That's this one. Good. It just needs to sit there. I still co-host from it.
Okay.
So that should be okay. So fun talking while sitting down.
Pardon?
So fun doing this while sitting down.
And I don't know what, I'll tell you, at work,
Mhm.
they gave us this podium. And that's where no, I'm not standing for an hour and a half talking about benefits.
Mhm.
I will move it back. Oh, oh. You get to plug it back in when you're done.
Yeah.
This
I'll make sure everything goes back.
Thank you.
And at least so far, it hasn't been so. I didn't destroy that much stuff. So hopefully everything still keeps working.
Cause the hours on, everything is in that way. Okay. Oh, no.
Good so far.
Okay. Did the weather was there? Okay. Cool. There's no fan. That's all okay. Yeah, that's just about this.
You have to turn around. You have to be away from. You can enjoy it. Okay, don't answer that. I told you to. I don't know worry about it. Oh, okay.
So you're a professor of mathematics and statistics at RIT.
Yes.
I didn't know that. My grandson
Uh,
won an award at high school.
uh,
When he opened, and he's going to major in statistics
uh,
at university, but he opens up the award at the award ceremony, and it is a letter from RIT offering him a large scholarship.
always nice.
It was nice, but
But where'd he go instead?
well, his top three schools are Rice, the University of North Carolina, Chapel Hill, and Cornell. And he's already gotten accepted to the University of North Carolina, Chapel Hill.
Gotcha.
So RIT is out. Yeah, but he's waiting to hear from Rice and
Gotcha.
Cornell. And he got accepted to a number of other schools.
Yeah, that'll do it. Yeah, when Layla applied to college, like she did apply to RIT because it would have been free. But she let us know early in the process she was leaving the state, come hell or high water. She was not staying.
I think North Carolina's got some warmth
Yeah.
to pull him down.
Those are all very good schools. Can't really go.
Also, he wants to, his love is sports statistics, and that's a Division I school.
Yeah, that's definitely one that RIT is not going to be able to compete with.
Let's let him settle.
Data kid who wants to make it, basically, he was making like business or economics. Type stuff. Things with AI, I keep saying AI is gonna, what is AI is gonna do?
I'll talk about it a little bit today. AI is an extremely useful tool, but woe unto those who think it does more than it can. A lot of the people talking about all that it can do are selling you something. Never believe a sales pitch when it's explicitly a sales pitch.
Unless it came from me.
Yeah, what it can do a lot of things, but it also can't do a lot of things. And some of the people talking about all of the potential are selling you something. Don't take it at face value, nothing.
Okay, I was just getting nervous in terms of what, especially in statistics, I just imagine AI being able to do everything and put together everything very quickly.
Oh yeah. There's a lot of things it can do. But its notion of creativity is very limited in very specific ways. Because of how it comes up. It has scraped the entire internet and basically the whole corpus of things that have been written down. It has all that in it. Its creative side is able to mix and match among that kind of thing, and nothing kind of outside of what's in the training set.
Yeah.
And that's a big limitation, as much as it has a lot of knowledge. And since it has a lot of knowledge, the wisdom is highly debatable, if that makes sense.
Okay.
And whether that's intelligence or not is very specific. Good morning.
I'm Jeremy Stephen's father.
Oh, hi. Hello.
I'm Mike.
Nice to meet you.
Nice to be back.
How
Yeah,
is
he
it?
gave me he's doing well.
Uh-huh.
Got one kid in Israel.
Uh-huh.
And, one kid about to graduate college 2 years early.
Like
I know.
before, I remember the baby pictures.
Yeah.
That's crazy.
He emailed me earlier.
Uh-huh.
Says, you gotta go to this.
Oh yeah, because my wife put out on Facebook, so
Wow.
yeah,
He might have known otherwise.
right. Yeah, that's great. Yeah, my group still like talks to his group all the time. It's been quite some time.
Well, I started reading his dissertation and got past the first 5 words and that was it.
So at my wedding, the Bethman lectured at University of Chicago. Like he's no slouch either, but he started reading the title just to show off.
Oh,
Things like that do that. It's very fun.
well, I teach at RMC.
Oh.
No, I mean, I teach it, you ever hear of Ozer?
Oh yeah, I know several people at Ocean.
Yeah, well, Victor's at Ozer.
Uh-huh. Yeah, no, that's fantastic.
I'm looking forward to it.
Oh, thank you very much. Yes.
I've been waiting this fun, oh yeah,
Uh-huh.
because it was announced.
Yeah, I have a throw out for you early in the talk, where you know much more than I do about like, it's like slide 2 or 3. This is all you, just so you know.
Supposed to do the slavery.
Yeah, it was supposed to be like at the end, but. Yeah, you can judge by the quote whether or not this is an auspicious thing.
If you think I'm handsome, stick around and look at the class. With both the friends. Well, other than the your most recent costume. About the last place. Business executive says. We only moved up here. But. Well, we moved up here.
I have the receipt for my pickup, I have to come to you to get the license check. I don't remember to do that.
You keep working on it.
So, I'll do it. Okay.
I don't know what I'm doing here, but.
We're collecting.
I don't.
Probably sitting at the window that people
Let's see. One of 3.
So Victor, just like old time's sake, but we have bagel and cookies. Yes, so the former microphone runner and assistant at the Manchester Science Cafe is now a first-year student at American University. And she just got back yesterday from a week-long trip to Lithuania. So she had a great political science and history. She easily could have, but she for the moment she wants to study politics and do good.
Very interesting.
I know that's a difficult combination sometimes. And her idol has always been Peter Ginsburg, so we'll see where it takes us. But yeah, so Layla, she was asking us sometime in the fall, should I take this class? They go to Lithuania. They go to Lithuania for like spring break. We're like, yes, you should very clearly go to Lithuania for spring break. She had a great time, of course, right? I was teasing her though. Lithuania has come a long way. Now, when you drink kvass, they give you your very own glass. You don't have to drink out of the communal glass from the club. As it drives around, now you get your very own glass of kvass when you're there.
At one point, she was not, yes, but,
Oh, there'll be more. We don't have enough cords scattered around, so I'm just gonna add a couple more.
Yeah.
Interesting.
Yeah. Oh, okay. I had a priority. I started over. I have my priority. Not necessarily. You're going to nice to spend. Yes, so if you start to do it. That's not.
Remove responsibility. No, we just. You know.
Sorry, I just want to make sure that I didn't kill the Zoom, but my phone tried to join, so we should all be good. One?
The owl on.
What?
Wow.
Audio's on.
Video.
Oh, the video's just off. There we go.
Yep, the links
There
are.
we are.
Here you go. Think we're good? Wait. Remember hitting, see, if you see.
Jennifer.
People are coming in from the waiting rooms? Who wants to start off with the crowd mic?
Correct.
Who thinks they've got the first question?
Participatory.
If nobody else, you can hand it to Esther because I'm gonna need her within the first couple slides.
Okay.
Oh, me, that's my first couple of jobs all the time. Thank you. You're welcome. Right.
I think we're all set up. Sorry, I wander when I talk, so I'm gonna just try to stay out of the way of the TV screen as we do this. Everyone can hear? Perfect. Good morning, everybody. Welcome to Whole of the Bagel. Hopefully this is a more auspicious day than it has been on this date at times in the past. Since this is a talk about, in part, free will, which we're probably not going to get to, in all honesty. I decided to go with a quote to celebrate the day and the events that have happened today in the past. So I'll leave that there for you right now. Just to introduce myself, hi, I'm Josh Faber. I'm currently the head of the School of Mathematics and Statistics at RIT and a member of the Center for Computational Relativity and Gravitation. That center was founded right before I started there by several colleagues of mine. I'll talk about them a little bit more later. As many people here know, I'm actually a Rochester product. I grew up in Pittsburgh, graduated from Pittsburgh Med in high school, left for college like many of us do, thinking I was never ever coming back here, and was gone for good. And after going around for many years, as much as Sheva and I enjoyed Champaign, Illinois, it's the kind of place that makes Rochester seem that much more pleasant to come back to. So we did 18 years ago with a 3-month-old in tow, who's now just back from a week-long trip, as I was telling some people, to Lithuania, where she went for a class because she's a first-year student at American University. My whole family seems to have abandoned me this weekend. Sheva's off with a cousin in Panama, and Charlie is on the Zika road trip to DC right now as well. So, but I'm here with all of y'all. So exactly. So, and I can't think of a place I'd rather be. So, for today, I wanted to talk about Albert Einstein, the universe, and free will. The warning right in advance is the fact that I've never actually given this talk before, and I always go way longer than I expect. So we may or may not get to the free will part at all. Yeah, bonus slides, we have bonus slides. We should be able to kind of get through at least some of the rest. To make this more fun though, please do interrupt with questions the whole time. That's more fun. Victor in particular can say that I used to co-lead the Rochester Science Cafe we met at Barnes and Noble. We had people from RIT, U of R, other places, give talks. And by the time we kind of hit our stride, we used to tell people for an hour-and-a-half talk, prepare about 15 minutes of pre-prepared material, and the audience will basically ask questions for the rest. And sometimes people didn't even get through 15 minutes worth of their own material, and the questions just took over. So to bring back that spirit, if anyone has a question, please just grab my attention. We'll put it on the mic and go. Well, let's check with Zoom. No, it's still trying to join. So let's give hope. So Albert Einstein. Not only a famous scientist, but I, like many people, own the t-shirt. I think you could argue, he really is the singular physicist of the 20th century. I have trouble naming more than three physicists who, based on a picture alone, people would be able to kind of identify. Newton, Hawking, and Einstein.
Okay.
I think are the three. I think I would recognize more pictures, or people who study the sciences would recognize more, but from the public perception, I think those are kind of the big three. He's possibly the singular physicist, the singular scientist, possibly, of the past many hundred years. As we'll talk about today, I think that reputation's probably earned. He really deserves that kind of place, certainly in physics. Rather than, since we're not going to get through even all the slides today in all likelihood, there's a lot of great reading material about Einstein. I have copies of several of these. The biography by Walter Isaacson is probably the most famous recent one. I have to admit, I haven't actually read it, but I've only heard great things about it. Personally, I've always kind of appreciated Subtle as the Lord by Abraham Pais. He's a practicing physicist of some renown in his own right, who knew Einstein personally. If you would like a biography of Einstein that has differential equations and integrals in it, this is definitely the way to go. And I will, even if not tripping over the cord, pass that one around. The Isaacson book you can find. Everyone's welcome to crack it open and take a look. I'm not kidding. There really are equations and derivations in there. He was a physicist. He's trying to explain Einstein, from the physics sense. One thing that's probably worth mentioning, I'll not pass this one around because it's a little bit beaten up over time. Einstein himself was also a fantastic writer in his own right. He writes with that kind of well-educated, well thought out writing style that you tend to find from certainly, people from the first half of the 20th century who had a good, strong kind of education in a broad sense. He's a fascinating writer in his own right, both in German and in English. I think if I remember right, The World as I See It was written in German and then translated. That's the earlier one, and Ideas and Opinions was the later one. He's a fantastic, he had complex and deep thoughts on a lot of stuff, and he was a great writer, so you can just read it from the original source, if you want. So there's no shortage of information about him, including from him himself. So don't just take my word for it. There's plenty of stuff out there about him. We'll see if this actually works. So quiz number 1. Was Albert Einstein good at math? This is a hopefully. We'll see if it plays. Wrong song. Tried that. There we go.
Einstein never good at math, but he found time down a curving path.
The found time down a curving path thing is a reference to relativity. We'll talk about that a little bit later. That's poetry. That's poetry. There's a claim here that about Albert Einstein and math that I think is pretty common, that basically he failed math, et cetera, et cetera. So the quiz, which you'll answer in a second, and then I'll comment. Was he good at math? Was this actually true? We'll find out. Eddie from Ohio, by the way, great folk act. They broke up a few years ago. Fantastic drummer. They're from Virginia. I can't explain it either, but they were a standard of the folk circuit for many years. I highly recommend them. Nope. Evidence, I'm not sure if this is for the prosecution or the defense.
Beats down in the snow. Everything's blazing a shot. What you see right now, it's a day comes to fall anyway. Yeah. All gets burned.
That's the band Counting Crows. More than anything else, this just indicates that, are people here familiar with Counting Crows? You can't make any sense of their lyrics at the best of times, and certainly not when they're talking about Albert Einstein. I'm not sure exactly what this is. I like the song, but I have no idea at all what it's trying to say. In honor of Purim, the song is Albert on the Beach for an Eggman. So it's in its own way a passing Beatles reference as well. But what it has to say about Einstein, I've never figured out in all the years I've heard the song. So was Albert Einstein good at math? I'll throw it open to y'all. Hands for yes.
Yes.
Hands for no. This isn't a majority vote, but the majority takes it. He was very good at math. I like Eddie from Ohio anyway. They're a great band, but on this matter, they're wrong, and some of the public legend is most decidedly wrong. He was both a solid mathematician, as well as an incredibly innovative mathematician. That was never the thing. Seemingly, the story comes from having failed his college entrance exam in 1895 when he was 16 years old. He applied to ETH in Zurich. He was 16 years old. He didn't fail it overall. He actually passed with some distinction on the math and physics parts of the exam. He failed the biology and language parts of the exam. He, like a lot of people, had his interests in those things he wasn't so interested in. He initially failed the biology and language parts. He passed a year later. This is kind of the mark 6 there means the best scores. You'll notice them for algebra, geometry, and things like that. Part of the other reason why this legend has come about. So a quote from Hermann Minkowski, one of his instructors in Zurich. I'm not going to try to pronounce the German, but that says he was a lazy dog, ein fauler Hund, a lazy dog, and didn't bother much with mathematics. He was not the most distinguished of all students when it came to being reliable for getting his work done. It wasn't lack of talent or knowledge. He just was a bit of a lazy student, and also kind of focused on his interests and not the things that he wasn't as interested in. I find myself kind of a little sympathetic with this. I'm a physicist who sits in a math department. There is a distinction between math and physics in outlook and approach. Einstein was very much a physicist. He was interested in explaining things, not the mathematics itself. Some of his colleagues, I think, especially back then, were kind of more naturally bridged that gap and were interested in the mathematics itself too. He never was, so much into that. So a little bit about Einstein. Always one of the more photogenic physicists, no matter which stage of life too. He definitely liked his fairly dapper tweed suits at this point. So he was born in 1879 in Ulm, in Württemberg, Germany. Moved to Switzerland in 1895 with his family. Went to ETH Zurich, a university that's still around and prominent to this day. He graduated in 1900. Got married in 1903 to Mileva Maric. Sorry, I have to let in my in-laws into the Zoom because they actually loaned me the dongle that I lost to connect everything up today and made everything today possible. Einstein got his PhD from Zurich in 1905. That's a big year. We'll be coming back to that very shortly. The big question I have that I'm not the right person to answer. So he was born in Germany in 1879. So I'm going to throw this one out to Esther Brill. I prepared the mic there. So in Germany, 1870s or so, anything going on for Jews in Germany, 1870s and things like that? Anything in the cultural milieu that was kind of going on? that whole kind of several decades worth?
I don't know.
English.
Germany, 1870s.
Well, just kind of the second half of the 19th century.
Immigration, is that what you mean?
Assimilation into broader society.
Assimilation, yeah. Oh,
As far as I know, the reform movement was founded.
here, in Germany. Oh, the reform movement.
I don't know when exactly it was founded, but
Probably more or less around that time, but I wasn't born yet, so.
yeah, so we're seeing the growth of the beginnings of the reform movement itself. You're certainly seeing much more assimilation than kind of previous centuries, as far as I understand it. This is kind of the rise of Yiddish culture as well, between Germany, the Pale of Settlement, places like that too. This is one of, I think, the flourishings of the Jewish community throughout history.
Josh, it was also a period of time when Germany was being formed, so you had multiple levels of assimilation. You had the assimilation of ethnic groups into the German society, and you also had the assimilation of the various German states, which had always been autonomous, into a new country. So there's just a lot going on that way. And I think the reform movement, because the reform movement in Cincinnati, which was created by German Jews who immigrated to the United States, was earlier than that, but yes, it was strong by that time in the 70s in Germany.
Right. So basically, this is definitely one of the more interesting phases of kind of Jewish history. I don't want to say Jewish American. There was also Jewish American history, but especially Jewish history. This is one of the great flourishings. There are many Jewish physicists out there. This is the time period where that kind of prominence does start to grow. When you take a look at older physicists, older mathematicians, it involved wealth, it involved privilege, it involved access to all sorts of resources. Kind of the great flourishing of Jewish physicists, as we kind of, which has continued to this day. I mean, this is roughly the time period in which this kind of thing would have started. This is Wikipedia's list of Jewish German physicists, not all Jewish physicists. This is Jewish German physicists from various time periods. If people are willing to go on a bit of a tangent, I'd be happy to go on a tangent. We'll get back to Einstein, I promise. There will be more quizzes. I hope everyone's been taking notes so far. But it turns out that I've got stories about 3 of them, all Nobel Prize winners. Mostly secondhand. One, I guess, is kind of firsthand. So this is a list of Jewish German physicists from the late 19th century to those born in the early 20th century. So a few stories. To someone who's studied physics or mathematics, several of these, not all of the names will be familiar, but several of these names are fairly familiar. Some of these are the definitely kind of the more prominent physicists in history. Hans Bethe was a longtime professor at many places, including Cornell University. When I was an undergraduate at Stony Brook in the 90s, my advisor was a 70-something-year-old physicist named Jerry Brown. He was from North Dakota and had a bit of a sinus issue, but he would say, "So I like to work with Hans Bethe because I feel like a spring chicken compared to him." My advisor was in his 70s. Hans Bethe at this point was in his 90s. They collaborated on nuclear physics. Bethe is one of the great nuclear physicists in history. One of the top tier nuclear physicists of all time. This was towards the very end of his career. He still went into work every day in his 90s. But my advisor was in his 70s. Bethe was in his 90s. This is the 1990s. We had email by then, but neither of them was particularly technologically savvy as these things go. So they had a long-running fax collaboration still back and forth, but in order to accommodate emails, the times being what they were, both of them would longhand write out their emails, and then their secretaries would type them up and actually send them back and forth because technology, they were not going to catch up with the technology anytime soon. Beta also is the most famous random inclusion on a physics paper of all time. There was a physicist in the 1940s, a graduate student named Ralph Alpher, working with a Russian emigre, George Gamow. People come across George Gamow's books. I would have brought them, but they're at work, unfortunately, right now. He wrote 1, 2, 3 Infinity and Mr. Tompkins Meets the Atom, among others. Great writer. They're very accessible books from the 40s, 50s to kind of see what physics was like back then. So Gamow had a graduate student named Alpher, and they happened to do the work that explained where the chemical elements in the universe came about. This was just a formative paper in understanding how the universe is like it is. And Gamow, being something of a joker, realized that rather than just have the paper be Alpher and Gamow, they invited Hans Bethe to join them for what is still known today as the Alpha Beta Gamow. For those who know Greek, it was too good a joke to pass up. All practicing physicists still know this paper today as the Alpha Beta Gamow paper. It laid out how the stuff that makes us up and the universe came to be. The interesting thing about it is that Alpher was not happy about this. He was a graduate student. He thought by including one of the great physicists of the day, in addition to his advisor, he would never get the credit for it. He nursed a grudge about this for 50 years. Today, his role in the paper, his work on the paper is now kind of completely recognized. And the paper is probably more famous than it would have been had Beta's name not been on it. Not many physics papers have a name and their own Wikipedia page. This one does. So history eventually kind of fixed that one, even though it took a great deal of time. So that's Hans Bethe. Number 2, Jack Steinberger. He's one of the younger people on this list. I looked it up this morning. He was born in 1921. Emigrated to the U.S. while still in his youth. Eventually won a Nobel Prize. I've never met him, but I did go to grad school with his daughter. She was in my class for graduate school. So I went to graduate school with Julia Steinberger. The third one, and we'll get to him in a second, because this is the one I actually got a chance to meet and talk to, is Rainer Weiss, Ray Weiss. We'll come back to him, since he's the one I actually know. But again, this is just Jewish German physicists. This is not even a complete list, but it was certainly kind of in Einstein's day, this was a blossoming intellectual movement across Central Europe. It flourished, and then, in a way that was replicated possibly only in the United States in the middle of the 20th century, because of times and everything else. So a little bit about science. Einstein for many years worked at the Swiss Patent Office. This is kind of the famous thing there. He was working on physics at the time. He had a day job too. This was not the most common career path, but it's not kind of as odd as it would be today. Einstein's 1905 is still quite possibly the most astounding scientific year by one person ever. I can't think of anything that particularly comes close. Even Newton spread his research work out over decades. Einstein did much more than this. Let me explain why. That was the year he came up with special relativity. We'll be talking about that shortly. That's the kind of the science part of the talk. He came up with, even though it was never written in this form, he came up with the equation that we now know as E equals mc squared. Mass energy equivalence. You can turn mass into energy and vice versa. That led to nuclear blank. Nuclear anything that we're familiar with basically comes from their energy, weapons, and everything in between. Today, we would probably say that those are the 2 most important papers he came up with this year. I think they've had the longest running effects. Along the way, during the year, he published a paper on Brownian motion. Brownian motion is what was observed when people started having more powerful microscopes. It's basically, if you look at particles in liquid, the way it kind of randomly jumps about through what we now know to be kind of atomic collisions. He came up with a whole theory that kind of explained what had been seen up to that point. In some sense, it proved the existence of atoms, or at least gave the strongest evidence for the existence of atoms that existed to date. There was still debate up to this point about exactly the nature of materials at the smallest levels. This is the paper that basically locked down atoms exist, they're real, and we're looking at their properties. Kind of a massive development. He also published a paper explaining the photoelectric effect. If you shine a very intense high energy light, more than just visible light, something like ultraviolet or X-rays or things like that too, you see particles jump off of a metallic surface or some other kind of surface. It's basically that those particles are absorbing energy from the light, and it can ionize them. You can send out electrons from when you shine a bright enough light on a surface. It's a very simple equation. It's one equation to describe the photoelectric effect. It's actually pretty straightforward. It's far and away the least, in many ways, the least important of the four papers. It's the least impressive result to describe. It won the Nobel Prize. The other three did not. But he managed to win the Nobel Prize for the fourth most important accomplishment he had in 1 year. I can't think of anything remotely comparable throughout history. What?
He's only 26 years old.
Oh yeah, he was definitely a youngster at this. The Nobel Prize came later. There's some culture involved in it. He won the Nobel Prize, I think, in the 1920s, if I remember right. There was some politics going on into what did he get awarded it for? But it is strange that they chose, in some sense, the least. They could have given a Nobel Prize for any or all of these, and they chose, in some sense, the least memorable one to this day. I can't explain it. Shall we do some science? I promise that we'll all be able to do this. The biggest risk will not be difficult terms or things like that, is that I'm going to trip over all the cords in front of you here before today's experiments are done. Around RIT, you typically see t-shirts like this. We have several people in the audience. What are we looking at on the t-shirt? What kind of math? Some people here know what we're looking at. Would anyone like to yell it out?
Marsha, where are you?
Okay, so these are Maxwell's equations. These are the equations describing electricity and magnetism. We don't need to go into the details, but basically through the 18th and 19th century, many scientists studied electricity and magnetism. They realized that they're related phenomena. You can use electric charges to produce magnetic fields, and you can use magnetic fields to move electrons, basically. This was the start of all sorts of electric technology, not electronic technology, that's the 20th century, but certainly electricity and magnetism. Remember Ben Franklin's the 1700s, key in the kite. This was kind of the hot physics topic of the middle of the 19th century. And it produced what became a huge crisis for physics, and my job is to try to explain it. Question?
Did problems with like Nikola Tesla's because I know he was a big influence and I don't know how much Benjamin Franklin actually did
Right.
with Nikola Tesla.
So Nikola Tesla, so he would be later than because he's right around the turn of the 19th into the 20th century or early 20th century. He's probably still one of the greatest technicians of kind of electrical technology that we've ever had. He's famous for basically inventing alternating current technology as we know it today. That's what's coming out of the wall. Yeah, he kind of took advantage of the science. From the technical side, he's probably the foremost person I can think of. As far as kind of technical developments. But about 50 years later, because it takes time once people kind of work out the underpinnings to kind of work out how to do it. So in order to explain why our understanding of electricity and magnetism is so strange, we actually have to go back to the 1600s. I promise we're only going to go back for a second. Galileo Galilei, people have heard of him, and yet it moves as he was being excommunicated by the church. Even back then, he realized an important principle from physics. The speed at which you're moving doesn't affect experiments that you do. If you're moving at constant speed, the laws of physics still work. That doesn't sound like much. We need to do our first experiment. Is anyone good at approximating things? Ready? I need you to give me a number. I'll be the experiment. I need you to jump in. So how fast am I moving? 2 miles an hour. Jamie, metric. Come on, I'm a physicist. How fast was I moving?
Moderate speed.
A meter per second?
Are you including the speed of the rotation of the Earth?
For the win. Galileo in 1600 realized that we don't live in a geocentric world. He's Copernicus, the heliocentric models, even though not perfect, certainly they realized we were not at the center of the whole universe, right? That's the 1500s. Galileo definitely knew we lived in what at the time would have been thought of as a heliocentric world, right? What time of day is it right now?
Morning.
Here.
Morning.
5 after 10.
Why? Well, I mean, you can't tell by just looking at the sun because this is Rochester, but you know the time of day comes because the Earth rotates and it's where we are relative to the sun. The Earth has a circumference of about 25,000 miles, give or take. It goes around in 24 hours. Roughly speaking, at the equator, where Sheva basically is right now, you're going around at about 1,000 miles an hour. Just from the Earth rotating. Up in Rochester, it's more like 700 because we're about 40-something degrees latitude. But the Earth is rotating at 700 or so miles an hour. And for the most part, we don't see it, right?
You feel it.
When you're doing calculations, you don't take it into account because you don't have to. And this is what Galileo and others realized. You don't have to always worry about the rotation of the Earth because it simply doesn't matter for the experiments that they were doing. As long as you're moving in constant speed, it doesn't matter. Admittedly, we're not moving in constant speed quite. We are going around in a circle around the Earth. Is that the only effect? Remember, I said heliocentric universe. Is the Earth merely just rotating in place?
No.
Anything else going on? We're going around the sun even faster. Rather than try to work it out exactly, we're going around the sun too. There's more, but we didn't fully know it yet. We're getting there. We're moving very fast. If somebody wasn't on the planet and was just watching the solar system go around, you're watching the Earth spinning as it goes by even faster in its orbit around the sun. And we typically ignore that. It turns out that the reason we can is because even though we go around in a circle, the acceleration due to going around in that circle is very small. It does matter that you can measure. You can actually measure with precise instruments the what we would call centrifugal or centripetal acceleration from going around, but it's a very, very small effect compared to gravity, which we'll get to in a second. And that part is kind of basically like a rounding error, but the speed itself at which we're moving doesn't matter. You don't have to know how fast the Earth is going to do experiments on the Earth. That makes sense? When you're measuring how does an electric field changing, create a magnetic field, you don't have to build in how fast the Earth is going around the sun, or if there's more to it than that with what we now know as the galaxy. Galileo knew this in the 1600s. Maxwell's equations, it's hard to see here, but they predict that there will be waves of electricity and magnetism. And these waves travel at a speed which is given by physical constants, and that's the speed of light. Right? So Maxwell's equations immediately, once they were written down, essentially predicted wave-like behavior that in every way matched up with what we know of light. And obviously that's a huge problem. No one here looks troubled. Oh, let me try to explain one more time. Because of Galilean invariance, it doesn't matter how fast you're moving, the laws of physics are always the same. There is a speed of light which is a constant. No one's still troubled. Okay, so let's go into why this should be troubling. Was there a question?
No, I was saying we learned this in high school, Michelson-Morley experiment.
Right. In fact, there was an experiment that tried to measure the speed of light is constant with respect to what? And to explain that question, we'll see if this video actually works. Do not try this at home, please. What I want you to do, if this works, this is someone driving way too fast on the Autobahn. It's just do you see that car that just went by? Can I convince you it's going fast? Do you still see it there in the lane ahead of it? Do not do this at home. This is not what any of us should be doing. Still see that car with its taillights? Oh, sorry. Which direction is that car with the taillights on moving with respect to this driver? Backwards, because he's now going 180 kilometers an hour, and that driver just slipped backwards past him. That other driver is going a reasonable like 80 or 90 miles an hour, and not what 120 or so, because he's not as nuts. That car was going quite fast, but it appeared to slip by backwards. We typically measure speeds relative to something else. That's how things work. Physically, that's all we can really experience. The picture for Galileo, they didn't have trains back then, they had boats. If you're on a boat moving at constant speed, think of a river, not the ocean. We're not thinking about waves, we're just thinking about going flat. If you're in a boat on the river and you're inside and you can't see outside, you don't know how fast you're moving. Until you have some other information, there's no way to tell how fast that boat is moving from the inside of the boat. If the waves rocket, then you accelerate and you can tell that, but you're inferring how fast you're moving. There's no direct way to measure it. Possible when you're inside. The modern day equivalent would be, has anyone here ever fallen asleep in a car? When you wake up, yeah, not while driving, passenger in a car. When you first wake up as a passenger in a car, if the road is smooth, you don't know that you're moving. It's usually only when you open your eyes or hear the road noise that you will infer that you're moving. You can't tell with your eyes closed if it's quiet.
There was a series of, you hear yourself?
Yep.
That's why I need Esther. There are a series of accidents in England when the railroads were first created, where people were in the railroad cars, not knowing that they were moving at speed because they were sitting in their seats, and would walk out the door and fall and either kill themselves or maim themselves because of that very principle.
Right. When things are smooth, you can't tell your speed. You can tell acceleration. When the train hits the brakes or the car hits the brakes, that you can tell. It's actually worth mentioning, this is the whole point of general relativity, which we're probably not going to cover today. That's for next class's quiz. How do I know that there's gravity right now? Besides, like, the fact I'm not floating up, in what direct way, though, do we really know that there's gravity?
Feel your weight pressing against the seat.
Yeah, so, anyone sitting feels their weight against the seat. Since I'm standing, the only real evidence is the floor that's applying a force up through my shoes to me. That's all we experience for gravity, is not gravity itself. We experience the pushback of the thing where our weight is going into, right? Everyone here feels the chair beneath them. For all the Kabbalah things, I felt the chair and my place there too. You actually feel the chair, not gravity. That's general relativity, just so you know. So what I want to do today for this class is special relativity. It's the simpler one of the two. This is why special relativity? That would be a good. It's because we've broken physics, and I need to explain how that came about. We said that the speed of light is a constant. That's not a hard statement, right? You can measure it. It's like 300,000 kilometers per second. It's fast, but it's a number. We said, though, that the speed at which you're moving doesn't matter. That leads to a principle that goes against the video we just saw. If something goes 300,000 kilometers per second by me, and it's light, I'm attached to the Earth, we said going what, like 700 miles an hour? Because of just the Earth's rotation, plus the Earth going around the sun, plus everything else. If there was an observer sitting outside the Earth watching go by, not a satellite per se, because those are also going around the Earth and it's complicated, but if someone was just out there in space, just watching me go on by, you would expect that if I thought light was going at one speed, they'd measure something different. Because they're moving with respect to me, and you would think the difference in our speeds would show up in how things work. Baseball fans, we need rabbi hats here. How fast does an average fastball in the major leagues go, roughly speaking?
90 and 99.
90, some guys can now top 100 miles an hour. How fast does it go if you're sitting outside the Earth? Watching it go by. Well, we said that the Earth is rotating at 700 miles an hour, right? That means that if you watch the baseball, the main component of the motion, if you're going around the Earth, around in its orbit, and watching the Earth go by and not rotating with it, it looks like those pitches are going about 700 miles an hour.
What if you're throwing it the other way?
Well, that's actually important, right? You'd either add or subtract 100 miles an hour, depending on whether you're throwing east or west, and not have to deal with that if you're pitching north or south. At that point now, you have to discuss which way are baseball stadiums oriented, so that sunsets don't get in players' eyes, but that's a different talk entirely.
Those are flashlight instead of a baseball.
We're getting, I promise. We never measure speeds constantly. We only measure speeds with respect to our own motion. They're never the same for different people. For everything else you've ever encountered, it's the speed relative to the person making the measurement. Michelson and Morley, when they heard about this, decided they were measuring the speed of light with respect to the ether. What's the ether? It's the thing that light moves with respect to. And
Come on.
Yeah.
Come on.
So instead, Einstein came up with a different way of looking at it. And this is why he was brilliant, and this is why he was singular. And it's the fact that I can get it into 6 words. Einstein's brilliant idea, this is 1905, special relativity, says that the laws of physics, including the speed of light, are the same, or invariable. Invariable just means are the same. They don't vary For all inertial frames of reference, it just means people traveling at constant speed. I'm not trying to complicate things, right? If you're moving at constant speed, the laws of physics are the same regardless of that speed. This doesn't sound so, this is kind of just a principle of universality, that the game has rules. It's the strangest kind of assumption to make in all of physics. Let me remind myself what the next slide is. So we need to do a second experiment. Ready? Very impressive, very counting up and down, how far did the ball travel? I'll do it again, but it may not go as well this time. How far did the ball travel? Not total displacement. I want total distance traveled up and down.
4 feet, 6 feet.
4 feet, 6 feet. Depend. We can negotiate it. It was a few feet, right? Herb, tell me about the planet again.
It's rotating.
How fast did we say?
I
I think we said 700 miles an hour. How far did the ball travel if we weren't in the room and we were watching the Earth go by? Well, let's count it approximately. Ready? 1 Mississippi, 2 Mississippi. 1.5 seconds. You'd have to convert to feet per second. But in the 1.5 seconds, the planet's rotating at 700 miles an hour. That's pretty fast, right? The top baseball pitchers pitch at roughly 100 miles an hour. Anyone know how long it takes to get from the pitcher's mound to home at 100 miles an hour?
Fraction of a second.
It's a fraction of like it's a significant fraction of a second, but it's less than a second, right? We're moving 7 times faster, and that was about 1.5 seconds. That means that we covered hundreds, if not into the thousands of feet, because the Earth is rotating, and yet it just looks like that. No one here looks troubled. I'm showing you why this is so troubling, and you're. So, remember that we said that the speed of light is the same?
Josh, everything is moving though.
Right? And the speed of light being constant really is the problem. So let's go into it. Speed has a definition in physics. It's not complicated. I just want the simplest one. Speed is just distance over time, right? Speed of light is a constant. If you do the algebra, then you will find that the time elapsed with something, if it's moving at constant speed, is the distance divided by the speed. If you don't believe me, we do have former professors in the audience. Marcia, is time equal constant speed? No complications. Time is distance over speed. The units work, I promise, right? We have it from a collection of scientists and mathematicians here that formula is correct. Time is equal to distance over speed. And the speed of light is constant. You don't want to do this with a tennis ball. I need to set up an experiment. We can't do it here, but remember how we said from the inside of a train, the laws of physics look the same? This is Einstein's kind of favored way of doing thought experiments.
Yeah.
Imagine that we're sitting on a train in the middle of a train car. And I don't know if they had them back then, they must have had something similar. Take a flashlight, right? I'm gonna put a mirror on the ceiling.
Yeah.
Flashlight at the mirror and measure how long it takes for the beam to bounce back at me. The speed of light is not infinite. It is finite. It takes a certain amount of time for light to travel, right? So there's a certain amount of time the light takes to travel to the ceiling, up and back down to me. And if I had an accurate enough clock, I could measure it. And in fact, nowadays, people do. Rochester's one of the capitals of the optics world. Timing light is something that has been happening in Rochester for a very long time. Not quite this far back, but certainly for a while. If I'm sitting on the train, and it's moving at constant speed. I shine my flashlight, it goes up off the ceiling, comes back. The total distance traveled will be basically twice the height between the flashlight and the mirror, up and then down. And the time it takes is that distance, the distance up and then down, divided by the speed of light.
Would gravity in any sense come into play there?
Yes, but not for another 10 years, because we're not up to general relativity yet. Yes, and that helped motivate it, in fact.
Okay.
This was an important question that we're ignoring. Remind me that you asked that question, I'll give you a much better answer in a few minutes. Let's say the train was moving, but the doors were shut, so the person inside doesn't know. Somebody sitting outside the train sees the train moving. They see the flashlight turn on, but the mirror itself on the ceiling is going along with the train. I screwed it into the ceiling. It's stuck there. So what you see, if you're not on the train, is that the train itself is moving and the light takes this diagonal path going upward, but also with the motion of the train. And then it bounces back, forming kind of another part of the triangle, and the time is measured. Does anyone here remember their high school mathematics? Do you remember like the Pythagorean theorem and things about right triangles?
Yeah.
All I need to convince you of, do you see how this arrow marked C is the hypotenuse of a right triangle? All I need to convince you of, it's longer than one of the two legs of the right triangle, right? The distance you see, the light traveling, if you're sitting watching the train go by, is further than the distance than the person on the train thinks it went. Right? It's a little bit extra. It's very fast, the train doesn't go that far, but yet it moves, to quote Gallup. That means that if I'm sitting here watching the train go by, I think the light went further. The distance is bigger, but the speed of light is a physical constant that we already agreed is real and constant. That means it took longer. Marcia?
Yes,
Is distance over speed.
yes,
Distance bigger and the speed is the same, the time gets longer. Me sitting on the ground watching the train go by, I think that it had to have taken longer for that light to go up and back down. But the person here has a clock and they just did an experiment, so the only conclusion, this is Einstein's genius, is that his clock is slow. Because he's moving with respect to me, his clock is slower than it should be. A moving clock ticks slowly. But wait, it gets weirder. I'd say I have a watch too. And let's say I did the same experiment to the roof of the room, the train station, as I went by. According to me, the light goes straight up and down. According to him, it went at this angled path, and my clock is slow. I think his moving watch is slow. He thinks my moving watch is slow. Who's correct? Well, there's no absolute frame of reference. Someone's sitting outside, both moving at 700 miles an hour or more, watching from. The speed at which time moves depends on the motion of the person measuring it with respect to me. Time itself is not some kind of absolute thing. Time itself depends on the observer themselves. Is this a little stranger than what you... We have not done anything complicated. I literally introduced the equation, time is equal to distance over speed, and we've done nothing else, other than to note that for a triangle, one side's longer than another.
This all assumes that speed of light is constant and unmovable.
Yes.
Why is that a prerequisite of this? And where did that come from?
So the speed of light comes from Maxwell's equations.
Right.
Einstein made the radical decision, in some sense, to believe Maxwell's equations. To believe that they were true and work out the consequences of believing in them. It's not that they had to be true, but this whole theory assumes that this theory eventually kind of included Maxwell's equations. You're assuming that something is true and that something else is true. And rather than saying, oh, trying to combine them defies my understanding of how the universe works, Einstein was brilliant at taking diverse ideas and taking them to their logical conclusions, even if it was counterintuitive what combining them would say. That's the brilliance of this. Shall we make it weirder?
Josh Faber asked.
Yes.
So, has there been theoretical twisting of that equation to say time is fixed, but light is variable?
Weirdly enough, no. Not really. There are theories that people look at where speed of light itself can vary, but that's still kind of strange physics to say. No one's come up with anything that's compelling that makes that work kind of, if that makes sense. There have been experiments, by the way, to measure exactly this. There was an experiment called Gravity Probe B, where they put very sensitive clocks on planes, basically, and flew them opposite ways around the world and measured the time difference. You get a time difference for planes going eastward around the world and westward because the Earth is rotating and the velocities are different. With respect to the person measuring everything. So let's make it stranger. I've got 2 tennis balls, but there's a lot of cords here, so I'm not going to do the full experiment. I'm sitting in the middle of the train car, but I've already done the thing where I shine the light up. So let's do the other thing. I'm going to shine the light forward and back. But now, wait, hold on. The experiment, I'm going to record it. I need to change it. I'm in the middle of a train car. We're good with that so far? I need 2 people on either side of the room to shine a flashlight at me. And I'm dead center in the train car. Remember, I don't know if the train car is moving in it.
There you go.
There we go, right?
Oh.
If we had kind of the mirror image on the other side of the room by the bagels, and both sides of the room shine a flashlight at me at the exact same time, when does the light hit me? At the same time. If I shine a flashlight back, if I shine one flashlight to one wall and one flashlight to the other wall, when does the light hit the 2 walls? At the same time. But now let's go back to the person watching the train car go by. And this is where it gets a little bit strange. I'm going to stand in the middle of the train car and shine my flashlights, but the train car is moving. Do you like to your left or to your right? I'll give them the choice. To the right. The train car is moving to your right, my left. The hardest thing as a teacher is learning to say right and hold out your left arm. It takes forever to get right. So the train is moving to your right. As I shine, I'm going to shine my flashlights, but somebody's sitting not on the train. Paul here is approaching me, right? Paul is heading towards where I was. And if you're standing outside the train car and the speed of light is a constant, first the light goes off, but then the back wall of the train approaches where the light was shined from, and it hits first. Meanwhile, the front wall, the rabbi is running away from me as fast as he can, or as fast as the train can go. It's going to take longer for the flashlight to hit the rabbi because he's receding from me. It's moving with respect to the person watching the train go by. So it takes longer for the light to get to the rabbi. Someone off the train thinks the light hits Paul first and the rabbi second. If I'm on the train, I think it hits them at the same time. Who's right?
Oh,
Yes. Simultaneity itself depends on how fast you're moving. Different people moving at different speeds don't agree on what things happen at the same time. I haven't introduced anything other than the speed of light being constant and this kind of idea that the speed at which you move doesn't matter. We didn't do big equations. No integrals have appeared on screen. No differential equations were solved. This is just a consequence of taking some principles and figuring out what they imply for their logical conclusions. This was the genius of Einstein. So we've already broken time. Moving clocks move slowly. We've broken simultaneity itself. Different events happening at the same time is a relative phenomenon. It depends on the speed at which you're moving. I could break distance as well, but we won't do that here. In order, if I only allowed myself shorter words, I don't know a good synonym for inertial, so I had to live with this. But basically, special relativity says physics laws the same, all inertial, just moving at constant speed, observers. It's not that it was complicated. It's that you have to be willing to follow it to its logical conclusions, and they're weird. And so be it. One thing you realize when you start to study special relativity, it was not just Einstein. Einstein had the last piece. There was a whole set of things that it was built upon. Just in studying special relativity, you'll talk about Fitzgerald length contraction, Lorentz transformations, Minkowski space. Minkowski was the one who called him a lazy dog. Poincare symmetry. Don't worry about what these things are. Many different scientists of the day have their names all over special relativity. It was a group effort, largely led by German physicists in kind of that greater area. His insight wasn't to add in something complicated. It was to take the different diverse elements and finally be able to put them together into a single theory, even though the conclusions were highly counterintuitive as to what it would say. He contributed very little to any kind of new mathematics. What he did was kind of put together and believe the different results up to that point. He did some of the mathematics, but he basically, by combining them and then explaining what they actually meant when you put them together, that was the genius for special relativity. And one of 4 things he did that year, if you remember, he was doing some other stuff, including Nobel Prize winning work that we're like, that one's okay. Many of us wouldn't mind like having a Nobel Prize on one of our side projects if we could. Most of us are not so lucky. This is a list of the named things in general relativity. General relativity, the theory of gravity, that was the singular one. I can't think of a single idea in all of physics where one person made as fundamental a contribution to our notion of physics as general relativity, the theory of gravity that came 10 years later. There likely will never be another one. These days, physics is as much an industry as a profession. Nobody works alone anymore. It's very hard to come up with something that's singular all by yourself when nobody works by themselves. I don't have a single colleague at RIT who works by themselves. Graduate students, other colleagues, your dissertation advice, everybody works with people. This one is singular. There were other people who he discussed with, but this gravity was basically his idea, general relativity. 100 years later, it's still one of the linchpins of how we understand the entire universe. And he did the vast majority of the work. It's, if you ask me, the greatest scientific development possibly in history. I'm a physicist. I'm a little biased here, but it's like that. We're never going to get through the slides. We knew that was coming. We're probably going to miss the free will part. What time do we go through, by the way? 45 past?
It's relative. If you're standing.
So let's say, yeah. Like many a teacher, I'm gonna just start walking faster, trying to slow down the talent. That should do the trick. If I just kind of walk around in a faster circle.
Question over there.
Yes.
You choose 2 minutes on free will.
I can get there. Well, summarize. One thing that I wanted to mention, because this actually came up before the talk. Could something like AI replicate what he did? I'm saying this is a singular achievement. Could AI replicate this? No, not at all. If you think it could, you're being sold something. AI, Google Gemini, ChatGPT, Claude, they have the advantage of basically the entire corpus of human knowledge has been either, depending how you think about it, uploaded or stolen and uploaded to their systems. I'll leave the ethics of that for a later discussion. What they're very good at doing if I can actually use the mathematical term, they're very good at interpolating from the world's largest data set. Given a huge amount of data, they can essentially average out amongst that kind of thing. They can take the patterns of words in one source and use them to express an idea from a different source. They can combine different things within the thing. The key reason why AI sounds impressive is because the corpus of human knowledge includes more knowledge than you have, or I have, or anybody has. So it always sounds really cool when it knows about these things because it scraped all of the internet in order to build that up. The second you start asking AI a question about what you know better, you begin to realize it took something that you're familiar with and is now kind of combining it with different styles from elsewhere, and that's how it's producing its results. The reason why college students think it's so brilliant is because it can do homework problems. The reason it can do homework problems is not because it's intelligent. The reason it can do my homework problems is because it already includes my homework answers in the data set. Or if I pattern them exactly like it, it can change the numbers and follow the same exact pattern. Try to have AI do something.
Somebody already did the
Yes.
problem.
It is amazingly good at doing what has been done. The main use case for AI seems to be having AI write things for people who don't want to write them, so they may be read by people who don't want to read them. It is far from, it is not creative in any way that I think we as people would call creativity or innovation. And the problem is that it's not just a matter of now. The very models that they're based on, predictive language models, basically what, to some extent, what is the next word, thought, sentence, fundamentally involves using the training set and living within it, not finding new things. It's not creative in the way that humans have been forever.
That's current. And having come from the high-tech industry, that changes 10-year cycles. And what will eventually happen with AI is what will eventually happen with AI is AI will recognize the errors within what we have come up with. And then give us back the fact that that's an error and allow us to now make a new discovery.
Right.
Until eventually AI will have the ability to make those discoveries. Now, whether that's in our lifetime or not, we don't know, but it's going to move very rapidly to that point.
The big thing that is missing right now is that the models that themselves are being used right now are not the right ones to do that kind of thing.
Correct.
What happens in the future, all bets are off. The existing models won't be the ones to do it. To add a side-eye reference, AI could never write the Song of Songs. It would never in a million years come up with the ideas that you find there. It's not built for it. It can now write a poem like the Song of Songs, but only because the Song of Songs is already written.
Well, I had a conversation with AI, ChatGPT, about the world as I see it. And in the midst of that conversation, it cut me off with a bunch of red letters, just as by the by. And the reason was that I committed the sin, according to ChatGPT, of using the name Einstein and Judaism together. Yeah, no, you try it and you'll find the same thing. So the conversation with ChatGPT about the notions of God, and don't ask me how, I don't go on ChatGPT all the time, but this just happened. I was very interested in how brilliantly, I did ask her the question and it brilliantly created a sense of relationship, very much as any physician in the room would recognize one can do this. So I began asking questions. So it has scraped the internet, but the internet is not evenly distributed in the data.
Right.
And how we are permitted to speak is very, very limited. So I just wanted to throw that in there because where the fuck else was I gonna say that I know picture?
It's basically quoting back at you in a sense, in a way that it takes a second to realize, not creating, but quoting back. We had a request for free will. So there's a whole nother talk that we can skip by.
Give us some Latin will, Josh.
Let's do some free will. Einstein's most famous quote, interestingly enough, is about randomness and not so much religion. God does not play dice with the universe. He wasn't talking about God, he was talking about dice. He's talking about quantum mechanics, how particles work. And his basic idea was that he didn't like the idea that things were random and unpredictable. Non-deterministic. He was very deterministic in his thinking.
I would disagree. I would say he accepted non-determinism. He didn't like it, and that expresses in a whimsical way. Part of the holistic universe, and then if you continue along this path, eventually you might get back to deterministic.
It certainly took him a while to kind of be able to.
But it's a whimsical way of expressing his desire, but not.
Right, but certainly he was uncomfortable with it for a long time.
Are you saying that he thought that God knew when to hold him and knew when to hold him?
Basically, so like a lot of physicists, he ends up kind of with the idea that if you've got the laws of physics and they're deterministic, then essentially the game is playing out in some kind of predetermined way. Quantum mechanics makes this weird. Quantum mechanics is the theory of small particles and things like that. It's famously probabilistic. There's a chance that things happen, and the chance that they don't. Just so we're clear, we're not talking, you sometimes hear about observers changing a system, and this is where people have kind of latched on and think, but we as people, as conscious observers, change the world around us. Got to be careful. When physicists talk about observers changing a system, that's true. It's largely about the fact that as an observer, in order to make a measurement, you put energy into a system, and that energy changes the system itself in some fundamental way. It's not about us being conscious. Consciousness plays no role in any of these things. It's about the fact that you can't observe a system without changing because of energy arguments. So here's we can might as well close off with this one. It's really not clear as a practicing physicist if we have anything like the free will that we think we do. It's very possible that as physical objects, even conscious ones, the laws of physics don't grant anything like free will. There are experiments that have been done in the past, and these are still endlessly debated, that seems to indicate that we start acting before we realize we've decided to act in a biological sense. It's just not clear. We wouldn't say that the computer has free will. We wouldn't say that the chair has free will. But it's hard to draw a bright line distinction as to where free will comes into the game. I can't identify for animals, bacteria, there's no clear distinction where free will and conscious. It's also not clear where consciousness enters into the system either, and that's kind of still one of the great unknowns. But Einstein himself was very. You don't have to believe him. He's from 100 years ago at this point. He was not a particular believer in the notion of free will, and from a physics standpoint, it's difficult to explain how that could come about. I'm not saying that we don't feel like we have it. We almost certainly do feel like we have it. Einstein believed in spirituality and all sorts of other things, and human behavior and everything else like that. But in some sense, there is a chance that we're acting as if we have free will, and that's the only world we'll ever know, even though we don't necessarily have it in the philosophical sense. And there's much more on that. If you want more about that, you should probably read his words on it, since I can always.
I just wanted to say that there's no way to do a scientific experiments to prove or disprove free will without a definition.
Right.
And I've never seen a clear definition of free will. In other words, we have limited definitions, limited by our minds, and we're doing experiments on ourselves. We don't know if a mouse has free will. We don't know if the bacteria has free will. And figuring out that is beyond us. How can we do it for ourselves?
I mean, we definitely have effective free will. We act as if we have free will, but what it means is in part, this is where physics and philosophy meet. To determine exactly what is it that our will shapes.
It's such an unattractive idea. Because from the point of view, I mean, I understand the ways in which. I don't know how to express it. The part of me that's shocking to you just knows very little about who I am, right? But that's the person that speaks and who I affect others. If I think I don't have free will, this voice that's talking, do I have a responsibility? And the answer is no. So it's such a problematic notion to put out there without defining terms better in terms of how we experience ourselves.
It's fiercely complicated, no matter how you slice it. I think I'm now over time.
Yeah,
That's what's gonna happen.
we have to, maybe next year, another one just about free will.
I would say about Josh. I'm a math person. I am not this person. I never have had this person. And I always have thought physics to be the most complicated in the world. You've taken a topic that is so beyond most of us sitting in this room. And at least I feel like I'm touching on it and understanding differences. So thank you.
Oh. I will say one thing to read Einstein. Very few people have ever had as much fun with physics and the universe and all the. He loved this kind of the whole him with the crazy hair on a bike is true. He had more fun with this than most of his peers, and in some way that probably directly contributed to his brilliance too.
Yes.
It's not a coincidence.
Thank you, Josh.
Remember the time travel guy?
Teach the kids. I have